This is our second lecture on X-ray production. At the end of today's lecture, students will be able to discuss the anode and its role in imaging. We will understand the Hill effect and how it is used in imaging. We will learn the differences between a mammography, CT, and interventional tube, and we will learn about high-frequency generators and understand the role of filtration and collimation in imaging. I will start with an overview of the X-ray tube assembly. The figure on the right shows a cutout of the X-ray tube. Its main components are the cathode and anode. The cathode is made of the filaments and focusing cap, and the anode is made of the target material, the stator and rotor. The entire setup of the cathode and anode is contained in an evacuated envelope called the X-ray tube insert. There is an output port for X-rays to exit and a cable socket for the high voltages for the cathode and anode. The tube insert is placed in an enclosure called the tube housing. Last week we learned about the cathode. This week we shall learn about the anode. The anode is the positive electrode in the X-ray tube. There are two types of anodes, stationary and rotating. The anode composition is usually tungsten or molybdenum metal embedded in a thick block of copper for the case of the stationary anode, or in some other support material like graphite for a rotating anode. We shall look at anode components in the next few slides. A stationary anode is shown on this slide. The copper block and target material serve three functions in an X-ray tube. Copper, together with the target metal, acts as an electrode to conduct electricity. It is also a mechanical support for the X-ray target and also a heat dissipator. Stationary anodes are used in dental imaging systems, some mobiles, or what is commonly called portable imaging systems. Stationary anodes will also be used in some special purpose units in which high tube currents and power are not required. On this slide, we have images of the rotating anode. When higher tube currents and shorter exposure times are needed, the rotating anode is used. The basic features are the same as that of the stationary anode. The rotating anode is a disc made of the target material, in this case tungsten, embedded in graphite and molybdenum as shown in the figure on this slide. The stem is made of copper and a molybdenum neck. The molybdenum neck is a low heat conductor and protects the bearings from heat damage. Molybdenum and graphite are used because they are lighter, making the anode easier to rotate. The circular geometry of the copper and target material follows the geometry of the disc. The anode has rotor and stator windings that form part of an induction motor. The anode is rotated by energizing the stator windings. General-purpose X-ray tubes are made of rotating targets. Specialty X-ray tubes like mammography tubes will commonly have a target of molybdenum or rhodium, principally because of their low atomic number and low K characteristic X-ray energy. Here is a larger view of the induction motor. The induction motor rotates the anode. It is comprised of the stator and rotor. By rotating the anode, heat is spread over a wider area, leading to a larger heat load compared to the stationary anode. Rotating speeds are between 3,000 to 6,000 RPMs for low speed and 9,000 to 11,000 RPMs for high speeds. X-ray systems are designed to energize only if the tube is at the correct rotation speed. On this slide, we shall look at the area of the target that is struck by electrons. This slide shows the anode in front view and side view. The size of area on the anode that is struck by electrons is called the actual focal spot and is primarily determined by the length of the cathode filament and the width of the focusing cap slot. The shortening of the focal spot length at the central ray is called the line focus principle. In the top right figure, the focal track is shown together with the focal area. In the left part of the figure, the focal spot true length is shown as well as the effective focal length. The projected focal spot onto the detector is called the effective focal spot. When target angle is made smaller, the effective focal spot size is also made smaller according to the formula shown. Diagnostic tube target angles are between 5 to 20 degrees. Different anode angles are shown on this slide. The anode angle is the angle of the target surface with respect to the central ray in the X-ray field. This slide shows tubes at different target angles and the influence of target angle on field coverage and the influence of filament size on effective power loading at a fixed distance from the image receptor. There is a trade-off between field coverage and target angle. There is also a trade-off between filament size and effective power loading. A large filament and small tube angle leads to a small effective focal spot and good power loading, but the field coverage is reduced. A large tube angle with a small filament leads to a large field coverage with a small effective focal spot, but power loading is reduced. For a large field coverage and good power loading, a large filament will be used, but the effective focal spot will be large, meaning there is geometric blurring and image degradation. So all these factors have to be balanced for the clinical task at hand. On this slide, we can look at effective focal spot size variation on the image receptor. The figure shows effective focal spot length varies with position in the image plane in the anode-cathode direction. Toward the anode side of the field, the projected length of the focal spot shortens, while it lengthens toward the cathode side of the field. You can see this more clearly depicted in the figure on the top right. This means spatial resolution will be better on the anode side compared to the cathode side. In the previous slide, I talked about effective focal spot size on the image receptor. The reason the effective focal spot is smaller on the image receptor is because of the line focus principle. The line focus principle results in an effective focal spot size much less than the actual focal spot size. The line focus principle allows high anode heating with small effective focal spots. As the target angle decreases, so does the effective focal spot size. An added advantage of small effective focal spot size is improved spatial resolution. Another effect associated with the anode is called the Hill effect. The Hill effect refers to a reduction in the X-ray beam intensity towards the anode side of the X-ray field. This is caused by the greater attenuation of X-rays directed towards the anode side of the field by the anode itself. The smaller the anode angle, the larger the Hill effect. The figures on this slide illustrate the Hill effect. The Hill effect is important when one is imaging anatomical structures that differ greatly in thickness. The higher intensity X-ray is placed over the thicker anatomy. In mammography, the Hill effect is useful because the cathode side of the tube is placed over the chest wall to take advantage of the higher intensity X-rays on that side. Another consequence of the Hill effect is that effective energy is higher in the anode side of the beam. Here is an application of the Hill effect in general radiography. The second image shows a more uniform chest image obtained from placing the cathode side over the thicker anatomy. So this means the image is taken with the cathode end of the X-ray tube down. Let's now look at the protective housing that surrounds the X-ray tube. This slide shows the X-ray tube housing. The tube housing supports, insulates, and protects the X-ray tube inset from the environment. It's not shown in this figure, but between the tube inset and housing is oil that provides heat conduction and electrical insulation. In many radiographic tubes, an expanding bellows system allows the oil to expand as it heats up. In X-ray tubes used in interventional fluoroscopy and CT, there would be heat exchangers to allow for prolonged operation at higher power output without the tube overheating. The housing also contains lead to attenuate nearly all X-rays that are not directed at the output port. A small fraction of these X-rays, known as leakage radiation, penetrates the housing. Let's now look at some special X-ray tubes. Mammography operation requires tubes to be designed to provide the low-energy X-rays needed for optimal mammography images. I mentioned earlier the difference in target materials used for mammography tubes compared to general diagnostic imaging. Recall that the most common target materials in mammography tubes are molybdenum and rhodium. The output port is also made of beryllium. Mammography tubes also have smaller focal spots relative to general diagnostic tubes. Typical effective focal spots are 0.1 mm and 0.3 mm. Mammography tubes are also operated at low kV, typically between 25 to 35 kV. With digital detectors, mammography tubes are now available with tungsten targets with rhodium, aluminum, or silver filters. These tubes can be operated at higher tube potentials. CT and interventional X-ray tubes require high instantaneous X-ray output and high heat loading and rapid cooling. Also, CT X-ray tubes are part of a gantry that is sometimes capable of 0.3 seconds rotation times about the patient. This places a lot of mechanical stress on the X-ray tube. CT tube designs usually have enhanced bearing support for the anode, as well as different cathode designs to help the tube handle the high stress forces. The figure on this slide is a novel design from one CT manufacturer. This design has a cathode and anode as part of a metal vacuum enclosure that is attached to externally mounted bearings and a drive motor to rotate the assembly. The electron beam in the tube is also steered electromagnetically to distinct focal spots on the anode. This is called a flying focal spot. This allows slightly different projections to be acquired. The anode is also cooled directly by oil circulating within the housing, giving it a high cooling rate. I showed this figure in a previous lecture when I spoke about the cathode and focusing cap. On this slide, we are looking at a specific application X-ray tube. For interventional radiology, pulsed X-rays are used to reduce patient dose. Pulsing of the X-ray beam is achieved by using the grid control on the focusing cap. By applying a negative 4 kV potential to the focusing cap, the tube current can be stopped. By switching this potential rapidly on and off, the tube current can be pulsed, leading to the production of pulsed X-rays for interventional applications. The rightmost image shows a pulsed focusing cap with grid bias. On the previous slides, we talked a lot about the anode of the X-ray tube. The complete tube consists mainly of the cathode and the anode in a high vacuum glass enclosure. This module is called the X-ray tube insert. In the next few slides, we shall look at powering the tube for X-ray production. We shall start with the X-ray generator. One might ask why a generator is needed. To answer that question, we need to know that the voltage coming out of most outlets in a hospital is less than the kV range needed to accelerate electrons in the X-ray tube. Most hospital outlets may have up to 480 volts. So the principal function of the generator is to provide a high voltage to the X-ray tube. This is achieved by using transformers. A transformer is a device that steps up or down an alternating voltage. X-ray generators consist of several transformers. For an X-ray tube, a transformer is used to step up any voltage coming out of the wall outlet to a high voltage of up to 150 kilovolts. On the next slides, we shall talk about the types of generators as well as different transformers. There are different types of generators used in X-ray tubes. Some older X-ray tubes may have three-phase generators. Modern X-ray tubes will most commonly have high-frequency generators. A single-phase generator means a single AC waveform. A three-phase generator means three voltage waveforms. Another component of the generator is the rectifier. A rectifier consists of several diodes. A diode is a circuit element that allows current to only flow in one direction. It is like a one-way valve. In an X-ray tube, the rectifier converts the AC waveform to a DC waveform that can then be applied to the X-ray tube to accelerate electrons. The bottom figure shows a half-wave rectified waveform. Half-wave rectified means the rectifier only allows half of the waveform to pass through. This waveform is not useful because there are times where the X-ray tube is not producing X-rays. The top figure shows several waveforms. A three-phase is a better waveform than a single phase because the voltage applied across the X-ray tube is nearly constant, never dropping to zero during exposure. You can understand this better by looking at what is called the voltage ripple. In the top graph, both half-wave and full-wave rectified waveforms have a voltage ripple of 100%, meaning the voltage varies from zero to its peak. For the three-phase, six-pulse waveform in the figure above, the voltage ripple is only about 13%, meaning the voltage supplied to the X-ray tube never falls below 87% of its maximum value. This is better than a single wave. You can see why the high frequency and constant potential waveforms are the best. Let's take a closer look at the transformer. A transformer has two distinct electrically insulated wires wrapped around a common iron core. When input AC power is applied to the primary winding, an oscillating magnetic field is induced. The changing magnetic field induces a voltage on the secondary winding. This voltage is magnified by the number of turns of the wire on the secondary. So we can say the voltage induced on the secondary winding is proportional to the voltage on the primary winding and the ratio of the number of turns of wire windings on the secondary and primary. This is called the law of transformers. The formula is shown on the top right. Note that the power in the primary and secondary are the same. On the next slide, we shall look at the types of transformers. There are three main transformer arrangements. When we look at the diagram of a transformer, we think of the primary as a left winding and the secondary as a right winding, unless it is labeled otherwise. A transformer with number of turns of the secondary greater than number of turns of the primary is called a step-up transformer. A transformer with number of turns of the secondary less than number of turns of the primary is called a step-down transformer. A transformer with an equal number of secondary turns and primary turns is called an isolation transformer. The high voltage selection of an X-ray generator contains a step-up transformer, typically with a primary to secondary turns ratio of 1 to 500 to 1 to 1000. A transformer can also be arranged as an auto transformer. On this transformer, a single primary wire is wound on a soft iron core. The primary wire is tapped at various points to simulate step down. By reversing the connections, you can use this as a step-up transformer also. By having several tapping points, you can have what is called a switching transformer. Here is a modular arrangement of the X-ray generator. The module includes the high voltage power circuit, the stator circuit, the filament, focal spot selector, and automatic exposure control circuit. Let's look next at a particular generator. A few slides back, I mentioned that there are several X-ray generator circuit designs in use. I mentioned the single-phase, three-phase, constant potential, and high-frequency inverter generators. The high-frequency generator is the state-of-the-art choice for diagnostic X-ray systems. This figure shows the components and circuit diagram of the general-purpose high-frequency inverter generator. In the high-frequency generator, a single-phase or three-phase power input can be used. I will describe the process of generating the high-frequency, high-voltage potential in the next slide. Here is the process that leads to the production of the high-frequency DC waveform for an X-ray tube. The input voltage from a single-phase or three-phase waveform is first rectified, then smoothed to create a DC signal. The signal is sent to a high-frequency inverter that converts it back to an AC waveform of high frequency. The high-frequency AC waveform is input to the high-voltage transformer. After stepping up the voltage, the signal is rectified and smoothed, resulting in a nearly constant output voltage as shown at the end. The principal advantage of high-frequency or constant potential X-ray production is the greater quantity and quality of X-rays produced. The radiation quantity is greater because of the greater efficiency of X-ray production at higher tube voltages. Another advantage is that single-phase or three-phase power can be used as an input. On the previous slides, we learned about the generation of the high potential across the X-ray tube. Let's now learn about how the duration of X-ray production is controlled. Timers are used to control the duration of X-ray production. Older timer systems were based on resistor-capacitor circuits and charge-discharge timers. These types of timers involve manual control because the user selects the duration for the X-ray production, and the timer stops X-ray production once the time selected is reached. In modern X-ray tubes, automatic digital timers are used. Digital timers utilize electronic switching circuits on the high or low voltage side of the high-frequency transformer or X-ray switching using grid control. Let's look next at the automatic X-ray control. Here is an example of an automatic exposure control unit. This system uses X-ray detectors placed behind the patient but before the image receptor to measure the X-ray output and automatically terminate exposure when the preset radiation target is reached. This approach is used for some pre-programmed imaging techniques. The X-ray sensor measures the actual amount of radiation incident on the image receptor and terminates the exposure when the proper radiation exposure is obtained. The advantage of this system is that it allows the X-ray device to compensate for patient thickness and other variations in attenuation at the point of imaging. The figure on this slide shows the AEC system. I want to draw your attention to the density control unit on the figure. This unit varies the dose by 10 to 20% depending on the manufacturer. It allows the user to select more dose or less dose as desired. Also, the user can select different sensor cells for different imaging tasks. In some cases, the AEC can fail. If this happens, a preset backup timer terminates the exposure. This safety feature ensures patients do not receive excessive dose. After learning about X-ray generators, X-ray production, and the control of X-ray production, we can now learn about X-ray technique factors used for imaging. An X-ray technologist can select various technique factors for imaging at the X-ray console. A technique factor that is selectable at the console is the kV. kV controls the beam energy by controlling the kinetic energy of the electrons in the X-ray tube. kV also controls beam penetrability. When, for example, 80 kV is selected, that means the X-rays produced would have a spectrum of energies ranging from 0 to 80 keV. Also remember that because of the Compton interaction, higher kVs lead to more scatter relative to photoelectric absorption. Another technique factor that is selectable at the control console is the tube current in milliamperes or mA and the exposure time in milliseconds. On some machines, the milliampere seconds MAS is selectable. The product of mA and exposure time is the MAS. If 200 mA is selected and an exposure time of 100 milliseconds is chosen, the MAS is equal to 200 mA times 100 milliseconds, which is 20 MAS. Higher MAS means more X-rays for image formation, which means better image quality, but also means higher dose to the patient. In general radiography, the technologist also gets to select whether to use the table image receptor or the wall receptor. We will talk more about this when we get to the projection radiography lecture on a different day. Now let's look at some quality and safety issues. I have talked about beam filtration in a past lecture in general terms. Let's look more closely at filtration. An X-ray tube has inherent filtration due to the glass or metal envelope used for the tube insert. There is also the filtration from the mirrors used to project the collimator area onto the image receptor. There is also added filtration that is used to improve beam quality. In diagnostic X-ray tubes, copper or aluminum are used as added filter material. The effect of copper and aluminum filters on surface dose is shown on this graph. In mammography X-ray tubes, molybdenum or rhodium are used as the filter material. The use of molybdenum and rhodium with like targets allows the filter to selectively reduce the X-ray photons around the characteristic peak so that the beam is more monoenergetic. We just talked about filtration on the previous slide. Once you have all that filtration in the beam, the question is, what is the beam quality? X-ray beam quality is characterized by the half-value layer. Half-value layer is the thickness of attenuating material needed to reduce the beam intensity by half. Half-value layer is a quantity we can measure, and it depends on the kV and filtration in the X-ray beam. A higher kV and more filtration means a higher half-value layer will be measured. This implies a higher quality beam. High-quality beams are more penetrating and contribute to image formation while reducing patient dose. Another safety feature is beam collimation. The X-ray beam area is limited by the use of collimators. Collimators are shown in the figure on this slide. The collimator area is indicated by a light field that projects onto the detector. The light field and X-ray field are aligned to coincide. This is done by using mirrors in the collimator. Collimators limit the X-ray beam to the region of interest. This protects the patient from receiving radiation in areas that are not of clinical interest. In some systems, there is what is called a positive beam limitation or PBL device. The PBL opens the collimator to the field size of an image receptor that is placed in the receptor holder. So the PBL automatically limits the area of the X-ray field to the useful detector area. This is the last slide, so we shall look at some questions next. First question. During imaging of a foot, the technologist places the cathode of the X-ray tube above the thicker part of the foot. The technologist does this to take advantage of what effect? The correct answer is heel effect. Next question. Which of these is not a benefit of the line focus principle? First choice. It makes the effective focal spot smaller. Second choice. It improves spatial resolution. Third choice. It improves heat loading. Fourth choice. It makes the effective focal spot larger. The correct answer is it makes the effective focal spot larger. Next question. The effect of a small anode angle is to 1. Cause a larger heel effect. 2. Cause a smaller heel effect. 3. Has no influence on the Hill effect. The correct answer is 1. Cause a larger Hill effect. Next question. Which of these is not a function of the protective housing of the X-ray tube? First choice, provides mechanical support for electrical cables. Second choice is a magnetic shield to protect electrons in the tube. Third choice provides mechanical support for the tube insert. Fourth choice contains cooling oil to conduct heat away from the target. The correct choice is 2. It's a magnetic shield to protect electrons in the tube. Next question. Based on what you know about the Hill effect, when imaging a chest, the best orientation of the X-ray tube is 1. The anode-cathode axis oriented left to right. 2. The anode-cathode axis oriented right to left. 3. The anode-cathode axis oriented vertically with the cathode up. 4. The anode-cathode axis oriented vertically with the cathode side down. The correct choice is 4. The anode-cathode axis oriented vertically with the cathode side down. This is the last slide of this presentation. Thank you for watching.